Hello students, Professor Smolny here, talking about Chapter 6, entitled Pathfinding, Allowing Agents to Properly Find and Follow Paths. So what are the key chapter questions for Chapter 6? What is a path network? What are the advantages of a manually generated path network versus an automatically generated network? When would you search for a path but not know the final destination? What search algorithms are appropriate when you know the final destination? When would pathfinding involve moving other agents? So, before we can talk about pathfinding, we really have to talk about path node definition. So this is the first of 4 different topics that the chapter is broken up into. And in general, in order to have a path, you need to have a node of different spots that the unit can move to. So in this case, there are 2 different regular grids that are here. One is a rectangular and the other is a hexagonal. Both have their pluses and minuses. The rectangular is very easy to understand from a programming standpoint. You can keep track of it in a simple 2D array. It's really simple to determine what the next node is. It's just one to the left, one up, one to the left and up, and so forth. And so it's easy to keep track of, but as far as distances, the corners here are a little bit further distance away than the adjacent nodes, so the ones that are directly above or left, or right or down. The other option that is commonly used is a hexagonal regular mesh. So in this case, there are 6 nodes around each node, and they're all equidistant apart, so you don't have to deal with the previous problem of having the corners that are actually slightly further away from the center unit. The trade-off is that a hexagonal grid is not easily encapsulated in like a 2D array. You can still use a 2D array, but you kind of have to use some trickery when you're trying to figure out exactly which node is the next node. So the fact that kind of each node is half a unit offset when you vary rows. They're not directly one on top of each other, right? They're kind of in between a little bit. But from an end user standpoint, and also from the perspective of certain algorithms, this is actually a lot better because of the same distance between each node, and because of the fact that in a rectangular grid, you tend to get zigzag movements if a unit has to move on a diagonal, or it'll go down one, right one, down one, right one, versus on a hexagonal grid where it'll actually look more intuitive because you can move left and right fairly easily, you can move along diagonals fairly easily, and it doesn't have that same sort of zigzag movement to it. Another way in which you can take care of defining a grid, a network, is to do it manually. And so this is a place where either you can automatically generate certain nodes to fill out a space, or manually a level designer could go in and place these nodes in where it makes the most sense to have them. This is used most commonly in first-person shooters, whereas the last 2 node grids are used primarily in real-time strategy games. Real-time strategy games, you kind of want to be able to allow the units to move anywhere within the space, whereas in first-person shooters, you want it to be more intuitive. You want to kind of generalize the different paths that are available, and so you would use an arbitrary grid that kind of takes care of the most common cases. Things like moving through corridors, moving through doorways, hiding behind cover, so crates or whatever, enemies that would be shooting at you might want to duck behind. And so this works really well for that. One of the next topics that the chapter is broken out into is the idea of path planning. So you've got your node structure, you know where your units will be at, you define the discrete locations where your units could be. Now let's talk about methods in which we can adapt the scenario around. So what are some common problems that we're going to run into when we're trying to figure out where we can go in their paths? So in this example, there are two different agents both trying to get to the same spot in the top middle example. So agent 1 and agent 2 are both trying to get to node A. Now obviously in real three-dimensional space, two objects can't occupy the same space. Two people can't be in the exact same space. They have to be relatively close by. So a solution to that problem is that one agent can actually be at the actual location where we told them to stay or told them to get to, and the second unit could be relatively close by. And the book goes to explain that in general probably it's best to take the spot that's the next closest to where the second unit started from. So one spot closer than they were trying to get to originally. This way they both have their own space, they're not colliding, and everybody's happy. Now this might present a problem wherein in that first situation we automatically assumed agent 1 will be able to get to node A before agent 2 could get to node B, so that basically there was no collision possible. Versus in the second instance, the bottom two examples, bottom two images, what happens if agent 2 is able to get to its goal before agent 1 can get to its goal, so that agent 1 actually has to navigate around it? So and agent 1 would have to do this weird kind of awkward path, or make a really sharp turn and then come back and make another sharp turn to get to its final destination. Doesn't really look nice. It would make a lot more sense in this case for agent 2 to go to node A and agent 1 to go to node B, because they wouldn't have to deal with this basically a conflict of three-dimensional space. And so the solution to this is prioritizing which agent goes where based on the proximity to the different locations. The third topic that the chapter goes into is the idea of path searching, or more generally what we call path finding. And so this is the problem of, I've got my node, I've got my starting point, I've got a series of spots that I want to go to, or one particular spot that I want to go to. What's the best route to get there? For relatively small grids, as in the case of the first-person shooter arbitrary grid, it makes sense to do table lookups, where instead of having to dynamically calculate what the distance is from point A to point B, you can just look it up in a table. Calculate it ahead of time. It's really, really quick. You have to do the processing ahead of time, but in the middle of the game you're not stuck there trying to wait for an algorithm to run through. Benefit is obviously the speed. Cost is that, for one, you need to do it ahead of time, but the second problem is that for a very large grid the table becomes unwieldy. It's roughly it's the square of the size of the grid, because obviously there's as many columns as there are rows. So if there's 8, it's an 8 by 8 table. If it's 100, it's a 100 by 100 table. You need memory to store all this. The other problem is that, that's really the main problem, in that you need to have enough memory for this. And so works well for small grids, does not work really well for large grids. Alternative to that is the idea of search algorithms. So these are, instead of having a lookup table, you're actually going to do some mathematical calculations in order to figure out what's the best possible route. Obviously they take a little bit longer, but they'll give you a better end result, and you do not have to